I'm Fabrizio, I'm the CEO of Nireos, and today I'm going to talk about our new hyperspectral imaging system. It's a hyperspectral camera, we call it HERA, and has the uniqueness, say, of measuring over very broad spectral coverage from the visible to the infrared in a single measurement. So just a few words on Nireos. Nireos is a company. We are based in Milan, north part of the city. We were born almost 7 years ago as a spin-off company of Politecnico di Milano University. And in these years, we've been growing. We are now up to 15 employees with more than 15 distributors worldwide. And we basically develop and manufacture solutions for spectroscopy, so devices for spectroscopy, such as hyperspectral cameras, spectrometers, detectors, and interferometers for Fourier transform spectroscopy. So in this talk, I will talk about hyperspectral imaging in particular. So what's spectral imaging first? I think that many of you already know. Just to clarify, here in the slide, you can see the difference between RGB imaging, multispectral, and hyperspectral. The differentiation between these three areas is the number of bands that the device can measure. So RGB is the simplest one, of course. Every camera is an RGB system that we are used to, so it measures 3 bands in the red, green, blue. A multispectral system refers to a system capable of measuring a discrete set of bands. Typically, this is something between 5 and 20, whereas hyperspectral means the capability of measuring the continuous spectrum for each and every pixel of the image. So many more bands, hundreds of bands. And so we are going to focus today on hyperspectral. So there are many different ways and companies producing hyperspectral images. Some of them rely on the so-called dispersive approach. So they follow the suggestions by this guy, Sir Isaac Newton, who discovered the light is made of different colors, the white light. And so these devices are based on gratings or prisms, such as common spectrometers based on gratings that everyone knows. But we have decided not to follow the suggestions of this guy, rather to follow the suggestion of this other guy, Fourier. So all our hyperspectral system, they work with a Fourier transform approach. This is the schematic of how Fourier transform approach works. This is depicted with a conventional and easy schematic with a Michelson interferometer. The idea for measuring the spectrum of light with this approach is to use an interferometer to create 2 replicas of the light. The 2 replicas of the light have a delay which is scanned, and by measuring the intensity signal as a function of the variable delay between the 2 replicas, one can measure this interferogram pattern, which is the autocorrelation of the light. And by performing the Fourier transform of this signal, you get the spectrum of the light. Now, these years we have been developing another specific interferometer. So we do not use a Michelson interferometer. We use our own interferometer. We call it Gemini. It is based on birefringence, and with respect to Michelson's interferometer, is much more compact and robust. So this allows us to work down in the UV region, visible region, and not only in the infrared, as common FTIR are limited nowadays. So this is the interferometer, highly stable and reproducible and accurate. That's a picture of the commercial device. We call it Gemini. So the Gemini is at the basis of our devices, either spectrometers or hyperspectral cameras. So the concept is the following, as I was mentioning before. You have an interferometer. It creates 2 replicas of the light. They impinge on a detector, which measures the interferograms, and the Fourier transform gives you the spectrum. So this is a spectrometer. So this is the product we have, in which we couple the Gemini interferometer with a single pixel element to provide a super broad spectral coverage from 400 to 4.5 micron wavelength. It's a spectrometer, is an FT, not FTIR, because it works down in the visible or UV. So it's an FT-UV VIS-SWIR, if you want. It employs the Gemini interferometer. So this is a single pixel spectrometer. But now, what happens if instead of single pixel photodiode, we employ an imaging lens or objective and a 2D sensor? Then we can parallelize the measurements of the spectra for each and every pixel of the sensor. so that each and every pixel of the sensor, like a CMOS, can measure the interferogram, and then performing one Fourier transform for each and every pixel of the sensor, you get your spectrum for each and every pixel. That is the hyperspectral data cube. So the sensor can be of any kind, can be a CMOS, CCD, InGaAs, whatever sensor you want. And so you can develop a hyperspectral system based on this technology. That's something we have already done by selecting already some sensors to be integrated in our commercial hyperspectral systems. So we coupled Gemini with the lens and the sensor. So we did develop a hyperspectral camera, the HERA V-NIR, with a silicon sensor. Then we have a model from 900 to 1.7 that we based on an InGaAs sensor. Based on an extended InGaAs, we have the extended SWIR camera up to 2.2 microns. And then we have brand new HERA VIS-SWIR using the new Sony sensor, the IMX990, which is capable of measuring the full range 400 to 1.7 in a single scan. So that's pretty revolutionary product. Nowadays, people that want to measure from 400 to 1.7, they need to use two different cameras and then try to stitch together spectra obtained from different devices. While here you have a single device, single sensor, single scan, so everything is much simpler. These are the main features of the camera. So it has a very high spatial and spectral resolution. The spatial resolution is simply given by the sensor, the lens, and the spectral resolution is given by the interferometer. It's a static approach, so you need to scan the camera while not moving anything else. This is not so typical in hyperspectral imaging, so in some applications this might be convenient. It has a very high optical throughput, so again, the Fourier transform allows you to avoid using slits or gratings, so you have a very high light throughput, enabling low light illumination conditions or fluorescence measurements as well. And it has a variable spectral resolution depending on the, it can be varied via software basically. The camera is suitable for remote sensing, macro imaging by just applying a macro lens for higher spatial resolution, and even more, you can couple the camera with any commercial microscope. And so you can upgrade your microscope into a hyperspectral microscope if you want to do hyperspectral imaging in microscopy. I will show you now an example of application where we used successfully this VIS-SWIR combination of spectra in breast cancer detection. So this is a big project and big application we've been involved with in the last period. The goal is to characterize ex vivo tumoral specimens right after surgery in order to give the surgeon a prompt quantitative answer during the operation. So the surgeon can have a really fast answer during the operation without waiting 2-3 days from the response for the anatomopathologist. So this can speed up and improve the process of operations. So in this example, I'm going to show you some real measurements with it. So this is us working with a camera right in front of a surgery room in the hospital for breast cancer. The sample is this one. So this is just an RGB image of the specimen. So this is a tissue extracted by the surgeon and cut in half to expose the tumor that was inside. The tumor is here where the yellow arrow is. Of course, by an RGB image, the tumor is basically not distinguishable from other parts of the tissue. But if you compare the RGB on the left with the hyperspectral on the right, this is the hyperspectral at a selected wavelength only, you can see that you have a much higher contrast, and here you can see clearly the two tumoral masses here. So by performing hyperspectral imaging, you can collect many spectra in reflectance in this case over such a broad range. And you can differentiate between fatty region, for example, from cancerous tissue. And the capability of measuring not only the infrared, but also the visible was essential to be able to discriminate tumoral tissues from some other tissues, typically fibrosis tissue that were otherwise not recognizable and distinguishable from the tumor. So this was essential. And thanks to that, we developed some models based on some spectral angle algorithm to automatically segment the image and to give the surgeon a prompt answer. So on the left, you can see the result of the algorithm applied on the 20-second measurement time with the camera right after surgery, compared with the H&E stained tissue from the anatomopathology department obtained after 2 days. And you can see that the match is pretty impressive between the two measurements. So this to demonstrate, this application, the capability of the device. Of course, this was just an example. The device is now being employed in a huge variety of applications, from agriculture. For example, you can measure chlorophyll absorption and color of leaves in the visible and conjugate this information with the water content, for example, in the infrared, or for cultural heritage, for pigment identification, for solar and material science, either in remote sensing or microscopy, for doing quality control. For example, you can map the band gap of your material. You can check the thickness of layers deposited on top of the different silicon wafers, of course, or in microscopy, if you want to really map your material and optimize the process for growing the next generation material for solar cells, such as silicon and perovskite tandem solar cells. Then microplastics, plastics, food inspection, microscopy. So many applications are unlocked thanks to this technology. Of course, depending on the application, the different spectral ranges might be more or less applicable or helpful, of course. So that's the conclusion of my presentation. I presented you a novel hyperspectral technology, and more specifically, a device based on this technology that allows you to measure over a broad spectral range, 400 to 1.7 micron, with a great sparse spectral resolution and very high light throughput. And the system, as I showed you, is really super versatile and can be coupled also with microscopes. So with that, I hope to manage to be on time, and I thank you all for your attention.